what we learned last time was that we can integrate functions of the form of this, and then some rational function like this, if the degree of Q is bigger or equal to the degree of P plus 1. And instead of cosine, we can have sine. We do this by considering the integral of e to the iz of p of z of q of z over some contour which depends on y and r, like this, and the contour is chosen like this, where this is minus r and this is r, and we're going up by height of y, like this. So this is r plus iy. Okay, and we have to do this in the smart way. If we take the limit, first the limit as y goes to infinity of this thing, and then the limit as r goes to infinity. Then this thing, a to the iz, of z over q of z, does turn into just the real part, which is the integral from minus infinity to infinity, e to the ix p of x over q of x dx. And then we read off the cosine from this as the real part of this integral, and read off the sine as the imaginary part. Yeah. Okay. Important thing to remember is not to try and rewrite this as the complex trig, and then work with that. Instead, just write this as e to the iz. That's the form in which it will work. Okay. So when we did these integrals around 0 to 2 pi, we rewrote the sine and the cosine as their complex. We rewrote them using our knowledge of the complex version of them. We don't do that here, so don't mix that up here. All right, so that's just a recap. Let's actually do it on some specific example. And our example is this one: integral from 0 to infinity of x sine of x over x squared plus 9 dx. So we will consider integral over this kind of a contour, gamma y of z e to the iz over z squared plus 9 dz. So I'm not going to go over again the fact that these parts will vanish as we let these limits go to infinity, first y and then r. So we're just going to take that as given, and we're going to calculate this guy. And if we choose r and y large enough so that we contain all of the poles inside this expression, then that thing will give us our answer. And that's all we need to do. Yeah? That's all we need to do. Because this thing, as you can see, has just got finitely many poles, in fact just 2 in this case. So for large enough r and for large enough y, we have that this thing will contain all the poles it possibly need to contain in the upper half plane, the only one of them. Yeah. And it's only true that in the limit as y and r goes to infinity that this thing is equal to this. But as soon as we have r and y big enough to contain our one pole, then the contour is going to be exactly the same no matter how big r and y is. Yeah. Cool. So we just need to focus on calculating this for sufficiently big r and y such that we contain the one pole. What is the one pole? Well, we have z squared plus 9 can be factored as z minus 3i, z plus 3i, right? So therefore, our one pole is here at 3i. Oops, this is 3i. This is where the one pole is. Yeah. So assume R and Y is big enough so that it contains 3i, and then let's figure this thing out. So the one pole we have is a simple pole. It's a simple pole, yeah? So let's simplify notation a little bit. Let's write f of z is this weird function, z e to the I z over z squared plus 9. So we want to calculate the residue at 3i of this thing, f of z like this. Since it's a simple pole, the formula for this is not too difficult. And this is the limit as z goes to 3i of z minus 3i f of z. Let's write out what this is. This is the limit as z goes to 3i. And what do we have? We have z e to the I z over this thing. Okay, so we're going to do this in one step. So when we multiply z minus 3i to this expression, since this thing breaks up into z minus 3i and z plus 3i, when we multiply this guy through, all we're going to have on the bottom is z plus 3i. Yeah? So on the bottom just we have z plus 3i. Are you happy with that? Yeah? Cool. All right, and then this is perfectly good because this top and the bottom are continuous, holomorphic at 3i, and there's no problem, so we can just stick in the values directly into this. So we're going to have 3i, e, and z is now 3i, so it's going to be minus 3 like this. Just minus 3 like this. And on the bottom, we're going to have 3i plus 3i, which is going to be 6i, so it's over 6i. So then this just turns out to be e to the minus 3 over 2, just like this. Yeah? Cool. So our residue is this real number. So therefore, this integral here, let's call this guy star. Make that bigger. So star is equal to 2 pi I times this residue at 3i f of z, and we've calculated it, so this is just equal to pi I e to the minus 3 over 2. Is that right? No, it's not right, because the 2's cancel. It's just equal to this. Yeah? Cool. All right, so if we look back at this expression here, yeah? So we said, okay, let's consider this part, and then the imaginary part of this part will be this thing over here, yeah? And our answer is that this guy is just imaginary. This guy is just imaginary. Do we believe that? Do we believe that? So this thing, if we wrote it out as the real and imaginary parts, sorry, not this thing. This thing, if we wrote it out as the real and imaginary parts, then what do we have? We have the integral from minus infinity to infinity, this cosine of x, p of x. Oh, but let's put the actual polynomial we have, which is this thing. I'm mixing things up. Right, sorry, let's do that again. Let's write this thing here, but let's write it as the integral from minus infinity to infinity on the real line, which is what happens when we take the limit as r and y goes to infinity. Yeah? So this thing in the limit goes to this thing. Yeah? It goes to this thing. The integral from minus infinity to infinity of x cosine of x plus I sine of x over x squared plus 9 dx, right? So this thing goes to this thing. So I definitely don't want you to think it's equal because we have to take the limit. So this thing goes to this thing in the limit, yeah? And then this thing is two integrals. It's this integral from minus infinity to infinity of x cosine of x over x squared plus 9 plus I, the integral from minus infinity to infinity, x sine of x over x squared plus 9. Yeah? This guy on the right is what we're looking for. But the fact that we have that the answer for all large enough r and y is just an imaginary thing, what does that tell us? What does it tell us from here? It has to be 0, right? Because this number is equal to this number if our theory is correct, right? If we did the calculation correct and the theorem is true, then this number is equal to this number. And this is just a complex number. Sorry, this is just an imaginary number. Yeah? There's no real part here. And this has a real and imaginary part. And the only way these numbers are the same is if this real part is 0. Okay. Do we believe the real part of this is 0? Yeah, it's what we call an even function, right? Cosine's an even function. So cosine is even, which means cosine of minus x is the same as cosine of x, right? Even. Yeah. And everything else here, well, not everything else, but this entire thing, which isn't cosine, this x over x squared plus 9, this is an odd function. Yeah? So a function is odd. So if f of minus x equals minus f of x, then it's odd. Yeah? Yeah? Remember this? Cool. So if we integrate an odd function from minus infinity to infinity, it's going to be 0. Yeah? Because the stuff on the right-hand side, whatever we have there, we have the negative on the left-hand side. Yeah? Yeah? Or at least if we integrate it in the sense of Cauchy principal value, as we integrate from minus r to r and take the limit. Yeah? Yeah? So, I mean, when I asked you what the difference was between Cauchy principal value and the other notion which you teach in calculus, you gave this example, and the reason it works is because this is an odd function. This is an odd function. Yeah? A simpler example would be this, also an odd function, where the Cauchy principal value, the limit as r goes to infinity, as we integrate from minus r to r, this is equal to 0, and therefore it exists, but if we integrate from 0 to r, it makes no sense. Okay, good. So this guy here is an odd function because cosine is even, x squared plus 9 is even, and this x itself is odd. So the product of an odd and an even function is an odd function. Yeah? So we teach this in calculus, or definitely teach it in calculus, and we sometimes give students examples like this, where there's nothing you can do in terms of applying the calculus techniques to show that this thing is equal to calculate this thing. Yeah? But you can just observe that it's odd. You can just observe that it's odd, and therefore it vanishes. Yeah? We'll probably give something like x to the 4 so that they at least know that this integral converges. All right, cool. So far we're happy because this is consistent with what we see when we expand out the integral we're trying to calculate. Yeah? And a corollary, not corollary, but as a consequence of this calculation as well, is that we have that pi I e to the minus 3 should be equal to the sine part, equals minus infinity to infinity x sine of x over x to the squared plus 9 dx like this. Yeah? And therefore, just getting rid of the I, we should have that this is equal to this. Yeah? Which isn't quite what we're looking for because the original problem was this guy. The original problem was this guy. Right? Yeah? And this is not quite the same because, obviously this is from 0 to infinity, but this guy, this entire function is an even function because x is odd, sine is odd, so producting to odd functions is even. So the integral from 0 to r is exactly half the integral from minus r to r. Yeah? So if we divide this thing by 2, we're going to get what we want, right? So we should have 0 from infinity x sine of x x squared plus 9 dx is equal to pi over 2 e to the 3. And that should be our answer. Everybody happy? And notice, as I'm going to keep telling you, just because it's so important, none of our stuff, none of our calculus methods are helpful for this. We cannot calculate this otherwise. Yeah? We cannot calculate this otherwise. Nothing I can think of in calculus would allow you to calculate this. This is completely new territory here. We're doing stuff we could not do before. All right, cool. Let's learn some more stuff. Okay, so there are situations where we want to calculate an integral, and we actually have a pole on the real line. And if we have a pole on the real line, then our methods just don't work in the same way. So suppose we want to calculate the integral from minus infinity to infinity f of x dx, but f has a pole on the real line. Yeah, but it turns out if we have a simple pole, or indeed any finite number of simple poles, then we can actually do this. And we have to think what we mean by this integral in that case. We have to think about what we mean. So just think about f as a real valued function. If we have a simple pole, then it's going to blow up in some way, right? It's going to blow up. So the simplest example is 1 over x. So 1 over x blows up like this. It blows up and blows down. Yeah? Yeah? So if we integrate 1 over x from 0 to 1, as you guys know, this is infinite. This doesn't converge. Yeah? But if we take a particular kind of integral where we're going to integrate from delta to 1 and also from minus delta to 1, and we add those up, and then we take the limit as delta goes to 0, that thing actually will converge, because these things that are blowing up will cancel each other out. Yeah? So let me write that down. So the limit as delta goes to 0 of the integral of minus 1 to minus delta. I'm going to put union here just to save writing delta goes to 1 of 1 over x does converge and is actually equal to 0. So this thing does make sense if we do this in a particular way. And this is kind of an analog of Cauchy principal value when we took to infinity simultaneously from the left and the right. Yeah? So in calc, we talk about improper integrals of type 2, where we take the limit towards this singularity and just from one side, and if this limit exists, we say therefore we have a meaningful integral. But we can instead do something like this, where we insist that we simply exclude a little ball around the singularity, or a little interval around the singularity. Yeah, because if we exclude a little interval around the singularity, then it is a meaningful integral. And if, as we exclude this little interval, then we can let the size of the interval go down to 0, and we still get a meaningful answer, then we say, okay, that's what we're defining the answer to be. So this is like taking the interval minus 1 to 1 and simply taking away the interval minus delta to delta, 1 over x dx. And this thing turns out to make sense. And the minus 1 to 1 could have been actually anything, right? It's just convenience. The point is that if we just take away a little neighborhood around the singularity and pass the limit, it's still going to have a convergent integral. Huh? So this is also called Cauchy principal value, but it's obviously in a somewhat different sense. And that's how we're going to deal with, so I'll call this Cauchy principal value. And this is actually really useful because it turns out there are many very important integrals we need to calculate where we have to think of it in this way. And that's how we're going to consider these guys. So if f is some function that has a pole on the real line, then we are going to simply take out a little interval around this particular point, get some answer, and then if, as we let delta go down to 0, we get a consistent answer, then that's how we define this integral to be. And that's going to be fine. That's going to be okay for us. Okay? So that's how this thing will make sense if we have a pole on the real line. Cool. So, how are we going to do this? So, using complex analysis, we will consider, or we want to consider, the integral from minus r to r, f of x, dx, or I should, now that I'm being more precise, now I'm talking about principal value, I'm going to write PV, principal value. So I'm not specifying where the singularity is yet, but I'm just saying that this is not the normal notion of an integral. This is where we cut out the singularity and then take the limit. So we want to consider this thing as part of a contour. Yeah. So we've been making the selections of a rectangle or a semicircle, right, where we went minus r to r, like this. If we did a semicircle, so we can do a semicircle whenever the degree of the rational function is minus 2. The degree on the bottom is at least degree on the top plus 2. Then a semicircle works. So if we did a semicircle, then what we would do is we'd have some issue because there's a pole right here. So we can't directly apply the residue theorem because the residue theorem holds true when we can have the curve in the part where it's actually holomorphic and makes sense, right? We have to put all of our theorems together. We're not allowed to take the curve through the singularity where it's not holomorphic. You know? So we can't directly go through this thing and have any meaning to it. So what we're going to do is we're going to just take a little bump around it like this. Just take a little bump around it. And that thing will miss our singularity. That thing will miss our singularity. And presumably there will be singularities in this upper half of the semicircle. So then we can actually apply the residue theorem to this contour. Yeah? Yeah? And what will that give us? That will give us the complex integral of around this particular contour. So if this thing is, say, delta, then this will depend on delta. Yeah, and ultimately we're going to take delta go down to 0. But if we do this, let me say that a better way. So let me start that again. So if we take this contour integral, then doesn't matter how small a neighborhood we take, then sure enough we can calculate what this thing is. We can calculate what this thing is. It's just the residue theorem. We just calculate the residues all here, right, and add them all together. That's no problem. We're going to let things go to infinity and to 0 in order for us to get something like the thing that we're actually looking for. Yeah, the thing that we're actually looking for. Yeah, and previously we learned that if we let this r go off to infinity, then the integral around this complex part right here, sorry, the integral around this semicircle part just vanishes and we don't care about it. Yeah, and that was the same thing we did when we had a rectangle. The sides just are not important. Now in this case, we can't do that. It's not so simple. We can't just say, all right, we've missed out this. Let's just ignore this semicircle. It's small. Let's pretend it's not there, because that's not true. The integral of the function on this semicircle doesn't vanish as we let the radius of this semicircle go down to 0. It just doesn't vanish. And we're going to see that. Yeah? So we'll have the answer to what this contour integral will be, and it will be the integral from here to here, then the integral around this semicircle part, and then the integral from here to here. And again, this semicircle part doesn't vanish. Okay, so let me write that down. So we'll find so I'm taking the simpler case now when I just have a semicircle for the top. Again, that holds true whenever we have the degree of the rational function is -2. This also works when the degree is -1, and then we have to take a rectangle, but I don't want to have too many indices floating around, so I'm taking the simpler case. All right, so we will take this thing, the integral around delta r of our function, f of z, dz, and for sure this is something that we calculate. This is the sum of the residues. Let me just put it in here. So that's the sum over I of 2 pi I times the residues, or 2 pi I times the residues at zi of f. This is something we can calculate. And as r goes to infinity, the semicircle part, which is harder for me to express in this way. So the semicircle, we will denote the semicircle as S of R. So this is the semicircle. Semicircle is S of R. As r tends to infinity, it will be the case that the limit as... So that's repeating itself. All right, that's stupid. Let me do this better. As r tends to infinity, the integral around the semicircle of f of z dz will go to 0, so we don't have to care about that part. No? But let's call this little bump thing here, let's call it, well, let's give this singularity a name. Let's call this z0, and then let's call the bump part here c plus z0. So that's the upper semicircle of radius, not r, delta, around z0. No? But this thing, put it over here, the limit as delta goes to 0 of the integral around this guy is not equal to 0. We can't just ignore it. We can't just ignore it. Yeah? So this would be completely lost. We wouldn't have any success with this. We wouldn't be able to do anything unless it turns out that we can actually calculate explicitly what this is. Yeah? But that is the case. We can explicitly calculate what this is. Yeah? Yeah? So it turns out, and I'll show you in a second, this thing, the limit as r tends to 0, c plus delta of z0, f of z dz, will turn out to be just pi I times the residue of f at z0. Okay, so it is like contributing half of a pole. It's like contributing half of a pole. Yeah? So this thing will actually be this quantity over here. So that when we take r to infinity, we'll have the integral along the real line from -infinity up to here. And then we'll have this part, which we know what it is, and then we'll have the integral from here to infinity. So if I write that in the language of maths, so taking r to infinity, we will have the integral from -infinity up to z0 minus delta. So z0 is on the real line, so this is a meaningful thing. Yeah? Of our function, f of x dx, plus this guy right here. Because we can't ignore it because it's actually there. And then the integral from the real part from here onwards. Okay, and all of that stuff will be equal to the Cauchy principal value. Sorry, will be equal to the residue formula answer that we have here. The sum over these residues over ZIF, like this. Okay. So that is just because we know that the upper semicircle will vanish. Yeah. And the game would be lost. The game would be lost unless this thing that has to be included in our expression was calculatable. But it is calculatable, as we'll see, and it's not particularly hard. So this is the integral from this to infinity, like this. So if this thing I just claimed is actually true, then we're okay, because this guy, which is messing things up for us, we can take the limit as delta goes to 0 and know exactly what it is. Yeah? So then we can just put it onto the other side. We can just put it onto the other side. Actually, I should do this right. So look at this carefully. If we go around like this, then this part here is going around in a clockwise way. It's going around in a clockwise way. Yeah? And we are going to think of this as part of the semicircle. So semicircle is part of the circle, which we go around in an anti-clockwise way. So that's how I'm going to do it in all the calculations. I'm going to do it in an anti-clockwise way. So this won't be, so implicit in this, if the orientation is anti-clockwise, this won't be like this, it'll be minus this. It'll be minus this. If I specify that I'm going anti-clockwise around the semicircle, which I will do because that's what we do all the time with circles or with anything, any closed curve. Yeah? So it actually minus this. Yeah? Cool. So then we can put this on the other side, and on the other side we're just going to add half of a residue. We're just going to add half of a residue. Yeah? And then as delta goes to 0, then these remaining parts right here this gives us exactly the definition of the Cauchy principal value that we're looking for. Yeah? So we'll be able to calculate the Cauchy principal value of this thing via this procedure, assuming this is correct, and we can actually calculate this. Is everybody happy? Okay, so what I really want you to do is not memorize this. I want you to be able to get this right formula from drawing this picture, from going, okay, I go around like this, from knowing that you can't just ignore this semicircle part, and the calculation I'm about to do will show you that. Yeah? Then looking at this and going, okay, well, if I go round anti-clockwise, then this semicircle part I'm going round clockwise. Yeah? So if I try and explicitly calculate it going anti-clockwise, I'm going to have minus this expression. Yeah? And therefore, the Cauchy principal value will be all the residues plus half of the residue, because I can explicitly calculate this when we take the orientation to be anti-clockwise, to be exactly half of the residue there. Yeah? So an easy thing to do is to just try and memorize the formula. And I'll be very upset if you get the formula wrong, because that will be my conclusion that you've memorized it, and I don't want you to memorize stuff. Memorization, again, is forbidden. Switch off your ability to memorize stuff. Yeah? Draw this picture for yourself. Just look at it, and then you'll see that this is natural. This thing is the only way it can possibly be. Yeah? Cool. All right, so I owe you this thing. And once we have this thing, then we have a formula we can explicitly use, and then we'll do an example. So let's, there's no space. Let's just erase the board and show you the thing I claimed. Proof of claim. Suppose f has a simple pole at z0. Then the limit as delta goes to 0 of the integral around the upper semicircle oriented anti-clockwise of f of z dz is equal to the residue of f at z0 times I times pi, like this, instead of I times 2 pi as we normally would have. Okay? All right, let's see why. So, proof of claim. Maybe I should put claim first, and then I should have put proof. Let me put claim, and now let me put proof. Okay, so since we have a simple pole, then we know it can be written of the form like this. F of z is equal to a to the minus 1 z, let me put it underneath maybe, z minus z0 to the power 1, and then just some holomorphic function g of z, where g is holomorphic. Let me do this better. So with this, for all z inside a small neighborhood, say B0, Z0, comma, where G is just a holomorphic function. It's just a holomorphic function defined in this neighborhood. Yeah, this is what we know. This is just from the definition of a simple pole, just using Taylor expansion. Right? Cool. So then we can try and explicitly calculate this integral like this. Yeah? Okay, let's do it. So take a parameterization. Equals z0 plus delta e to the it, like this. And then put it into this thing. So then the integral of c delta plus z0, f of z0 dz is equal to the integral from 0 to pi. It's half of the semicircle, right? Let me draw a picture. So we're going like this to this. Start here. Right, so this is z0 plus delta, and we end up over here. Yeah, so this guy is just integrated from 0 to pi. Yeah, so then we're going to have f of z of t, and then z prime of t. Let's put it here. Z prime of t is equal to delta I e to the it. So delta I e to the it. Like this, dt. And let's put in what our explicit form of f is. So this is the integral from 0 to pi, like this. I think I want to pull out the I and the delta Why not? So then if we explicitly put this thing in, then we are going to have a to the minus 1. And this is our parameterization, right? So when we take z of t and subtract z0, then we're just going to have delta e to the it on the bottom here. Yeah. And then we're just going to have, and this guy I'm not going to write out in terms of explicit form because I don't need it. Just put this as z of t, and that is this stuff, and all of this stuff therefore is multiplied by e to the it dt. Everybody happy? Yeah? Okay, so let's break that up. Let's pass this e to the it through. It's going to cancel with this, and this delta is also going to cancel with this. So we're going to have an I integral 0 to pi, and just a to the minus 1, and that is all we're going to have, right? So this cancels with this cancels with this, so that's all we have for this part. And then the second part, we're going to have plus I integral 0 to pi. And what we have g of z of t e to the it dt. That's this, and then what is left. Yeah? Cool. All right, so this part is fine. We are happy with this. Yeah, this part is fine. So that is just I pi a to the minus 1. And then if we look at this part, well, g is a holomorphic function, right? G is a holomorphic function. And z of t is getting closer and closer just to z0, where g is nicely holomorphic. Yeah? This thing is just a complex number of size 1, so we can take the absolute value through this thing and see that it's actually a small expression. So let me write that formally. Let's do it this way. So if we take the absolute value of this thing, c plus delta of z0 f of z dz minus this term here, I a to the minus 1 times pi, then what we have left is delta. Let's take the absolute value through this thing, integral 0 to pi, the absolute value of g of z of t dt like this. Yeah. And again, g is nicely bounded, right? Because we are close to this singularity where g hasn't got a singularity here. G is just holomorphic. Yeah. So by continuity, this thing is less than twice the absolute value of g of z0, so long as we let this delta be small enough. Do you see what I mean? Or shall I add the details? Yeah. So look. So for small enough r, then g of z minus g of z0 is less than absolute value of g of z0 over 2. Yeah. Maybe it's actually 0 itself, so plus any alpha, which is small. So let alpha be 0. I think it's not actually 0 because of a construction. Anyway, so this thing is less than this thing, right? So if we are integrating on this little ball like this, then the z are indeed sufficiently close so we can uniformly bound it. Yeah? So then this thing is less than delta times pi, the supremum of g. Actually, I can just do it this way, just the supremum of g on this semicircle like this. C plus delta of z0. This thing, as we've just seen, is bounded, so then this thing goes to 0 as delta goes to 0. Yeah? So that shows exactly our claim that the limit of this thing is equal to this thing, which is exactly what we said. A to the minus 1 is the residue. Cool. All right, so with this, we're in a position to calculate actual integrals f from minus infinity to infinity, where we have poles on the real line. In fact, we can have more than one pole. We can have any finite number of poles, and this thing would still work out fine. Yeah? Cool. Any questions before I raise the board? Is everybody happy here? Yeah? Everybody happy? Cool. All right. Integral from minus infinity to infinity of sine of x over x squared minus 2x plus 2, like this, dx. Let's do this guy. Okay, cool. So this is looking like our setup, right? We definitely have a singularity on the real line, yeah? Because just 0 itself is a pole, yeah? So we will consider the integral. I'm going to write C of capital R delta of e to the iz, because we've learned that this is how we get these trigonomic functions, and then z over z squared minus 2z plus 2 dz, where we have a contour like this. So notice that the degree on the bottom is 3, the degree on the top is just 1, right? So in this situation, we do not need to actually use the rectangle. This standard semicircle will work perfectly well for us. So I'm just going to use standard semicircle. Okay, I don't have an elementary explanation and I feel guilty. So now I'm not changing my mind. I'm now going to use a rectangle because I actually haven't shown you this, and it probably isn't as trivial as I said. So let's just do it this way. Yeah, so when we have, let's put it on here. So when we have something like this, where we have P of z over Q of z, okay, and we know that the degree on the bottom is at least the degree on top plus 2, and we integrate over the semicircle like this. Well, the length of the semicircle is r, right? And for very large z, then because the leading order terms of this thing are the dominant players, then this thing will decay like 1 over mod z squared. Yeah? So P of z over Q of z will be less than some constant mod z squared. We saw this, yeah? For all large enough z. Yeah? Do you remember seeing this? Yeah? So if we just look at this thing, then we're integrating something which will be less than a constant times r squared. So again, we're less than a constant times r to the minus 2 times something of length of r. So then the absolute value of this thing will be less than a constant times r to the minus 1. Yeah? So if we have this property that as we get very, very big, this thing, should be absolute value, this thing decays like r to the minus 2, then a semicircle is fine. Yeah? If we don't have that property, then we have to use special cancellations of our function. So when we consider this thing, e to the iz, P of z over q of z. Yeah. The reason this worked is because we had special cancellations allowing this to actually work out for us. When we integrated along here, because we're going along an imaginary line, we would have e to some minus something depending on t. So this thing decays incredibly fast as we go directly upwards like this. Yeah? And as we integrate across here, then because we are far enough away, the fact that p has got 1 degree less than this guy means that integral across this thing here is also negligible. Yeah? So this thing depended very much on this special structure of the cancellations that involved in this thing. And that allowed us to get away with the situation when we have just the degree on the bottom is 1 more than the degree on the top. All right, so backtracking on what I claimed, we are indeed going to play with 3 parameters. We are going to have r, y, and delta. And we are going to do this thing. Because this thing for sure we saw works, right? This did work for us. So we have r, this is r plus iy. This is r minus r, and this is minus r plus iy. And then this thing here is delta. Yeah? Cool. So let's deal with this thing. So what do we know? We have that if we take the limit as r goes to infinity, but first we have to take the limit as y goes to infinity of this guy, c of r, y, delta, e to the I z over z, z squared minus 2z plus 2. Yeah. Then the sides will cancel and the top cancels. So then this ends up being the integral from minus infinity to minus delta of e to the I x. Let's get the right pen. X squared minus 2x plus 2 dx plus, well, if we put the correct orientation, it's going to be minus, if we orient anti-clockwise again, minus this semicircle, this little semicircle right here. This is our guy, c plus delta of 0, like this. And now this is a complex integral, it's integrating around the complex. There's no longer on the real line, so we put this as z, not of x. Like this, dz. And then this integral, delta to infinity, this guy. Like this, yeah? Because of stuff we've learned. We've learned that the sides are not important when we take the limit, first as y goes to infinity and as r goes to infinity. So this is just previous stuff, yeah? Cool. All right, we also know that as soon as we include all the singularities, then this thing is an explicit thing we can calculate. We'll get to that in a second, yeah? If we just look at this thing, and this thing here, then as delta goes to 0, this is exactly going to be the principal, Cauchy principal value. Yeah? So this stuff in the red box is the stuff we want to actually get. Yeah? This is the extra stuff, so we're going to put it on the right-hand side. So let's call this thing star. So then star, no, let's do this better. So then this stuff here that we want to actually calculate, so we're going to put this in the proper way. So this is the principal value of this integral, which exactly means this thing is the limit as delta goes to 0 of e to the minus x over x, x squared minus 2x plus 2. This thing, now this thing is on the other side. And we also know in the limit as delta goes to 0 that this is actually going to be just half of the residue at that point. So this is going to be I times pi, the residue of our function. Let's simplify notation, and let's get rid of this. Let's simplify notation and let f of z be this function, e to the iz over this thing, z squared minus 2z plus 2. Okay, so this is the residue at 0 of f. Okay, and then all the other poles. Well, what poles do we have? If we look at the bottom, and let's see what we get when we factorize this. So z minus 2z plus 1 is z minus 1 plus I, z 1 minus I. Is that correct? Let's check. So multiply this by this, we're going to get, this is not 1, it's 2. We're going to get 2. And if we multiply these guys through, then we are going to get a minus iz. Oops, this is minus. We're going to get a minus iz, and then we're going to get a plus iz. So they will cancel, and we're going to have a minus 1 and a minus 1. So we get minus 2. So yeah, this is correct. Huh? Everybody happy? Cool. So our one pole inside our region is the sky, which is here at 1 plus I. 1 plus I is the one position we have a pole. So we have therefore just 2 pi I, the residue of 1 plus I of f. So the thing we're looking for, or at least what we're looking for, is the imaginary part of this guy, because this is actually our ultimate goal, is given by this thing that we can explicitly calculate now, because it's just a matter of calculating the residues. Everybody happy? Yeah? All right, cool. So, running out of space, let's calculate these residues. So what kind of pole do we have? We have a simple pole at 0, and we have a simple pole at 1 plus I. Yeah? So let's see what happens. So the residue 0 of f is the limit as z goes to 0 of z times this expression, f of z, which is the limit as z goes to 0. This is our function, so it is just e to the iz over z squared minus 2z plus 2. Yeah? And what's that? That thing is just e to the 0, which is 1. And this is just going to be just 2. So this thing is just a half. Yeah? Let's do the other residue. The residue at 1 plus I f, that's the limit as z goes to 1 plus I. And of f of z minus 1 plus I. F of z yeah, and what is this? This is the limit as z goes to 1 plus I. And then this thing will cancel one of these factors here. So the other factor, I've rubbed it off, so I have to try and remember. Let's put it up here so I don't erase it again. So how did we factor this? It was z minus 1 plus I. And then it was z minus 1 minus I. Right? That was the factorization, right? So then when we do this, limit here, then we're going to have this factor of z minus 1 minus I just vanishes. So then this will be the limit. I should put it down here. This will be the limit. I already have it here. This will be the limit of e to the iz, and then z, and then z minus 1 minus I is the only remaining factor, right? Because this guy knocks out this guy. Yeah? Cool. And then everything is nicely continuous here. So we can just plug in the value. So then we're going to have just e to the I times 1 plus I. And then we're going to have 1 plus I. And then 1 plus I minus this. The 1s will cancel, so that this will just be 2i here on the bottom. Yeah? And then what's this? This is e to the minus 1 plus I, and is there anything we can do with simplifying this? A little bit, I guess. So we can like this, and then that'll be minus 1 plus I. Like this. I don't like it that form. I want to put it on top. So let's multiply it by its conjugate, which is minus 1 minus I. Yeah. So if we multiply top and bottom by minus 1 minus I, then we're going to have e to minus 1 plus I. And multiplying this by minus 1 minus I, we'll have minus 2 on the bottom. No, we won't. Let's do that. We will have, so we have minus 1 plus I multiplied by minus 1 minus I will just be 2 on the bottom, right? Yeah, so it'll just be 2 on the bottom, so we'll have 4. And then we'll have minus 1 minus I on the top, and I'm going to write that just as like this. Like this. Yeah? Cool. All right, so that is this residue. And so let's put that together with this formula here. So just sticking it in here. This guy we found out was just a half, right? This is this thing. So we have just I pi over 2. And then this is 2 pi I times this somewhat complicated expression. So I'm going to write pi I over 2, this 4, let's put the minus over here. And then we have this expression here, e to the minus 1 plus I, 1 plus I. And what we need to figure out is the complex part of this thing in order to get the right answer. So we have to do a little bit more calculation. So what is this thing? So e to the minus 1 plus I is e to the minus 1 e to the I. E to the I is cosine of 1 plus I sine of 1. Yeah? So if we take, no, I messed it up because I actually want the real part, because this thing here is multiplied by I. So what I actually want is the real part, not the imaginary part. Okay, let's do that again then. Real part. All right, what's the real part of this thing? So the real part, it's when we multiply this by this, we are going to have this thing times this thing. So we have e to the minus 1 cosine of 1. And then this thing times this thing, which now becomes minus. So that seems to be the real part. Yeah? Everybody with me? Okay, cool. So then I wanna not erase. I want to have another board, so I'm gonna erase stuff. So then, what we actually want is the real part, sorry, the imaginary part of this thing. So let's put this in a box like this. And then the imaginary part of what's in the box, and we're just going to read it off. So it's going to be pi over 2 from this thing, and then it's going to be minus pi over 2, and then times this thing over here. So I want to put it down because it's too long. So minus pi over 2 times, let's put the e over here, 2e times cosine of 1, pen down, cosine of 1 minus sine of 1. Yeah. So finally, this guy, which is the thing we were looking for, well, I should write principal value, because it definitely has a singularity. So this thing is equal to this thing, and we are good. This is the correct thing. Okay? Cool. So, looks like we're out of time. Let me just go over the steps. We have some guy like this. We identify that it's got a pole on the real line. So we can't just simply create standard type contour. It's something we have to turn into this trig form. So we're going to write this e to the iz to recover this expression as the imaginary part of this expression. Yeah. We create our contour. We're going to use a rectangle. Yeah. We don't care about the sides or the top because we know the limit as y goes to infinity, then r goes to infinity means that they go away. Yeah. So then, taking the limit as r, y goes to infinity of this thing, yeah, we just end up with the integral from minus infinity to here. So we end up with this thing plus a little bump here plus this thing. Yeah. But we're going anti-clockwise, so as we do this, we notice we're going clockwise around the little semicircle. Yeah? And when we do the calculation, we did it anti-clockwise, our parametrization was anti-clockwise. So we remember, therefore, to put a minus here. This is a minus. Yeah? And then we have the part from delta onto infinity, which is this part. And then we see that this thing is the thing that we want. This is the thing we want. Yeah? So we put this on the other side, and then if you don't remember it, then hopefully it isn't too hard to calculate. This guy here is just going to be half of the residue at 0. This is the result that we learned, and looks like it's erased. Here it is. So this thing here is the contribution from this guy, and this thing here is just the residues of this complex function inside our contour, and there's only one, it's up here. Yeah? So at this point, if you've got this right, then it's just a matter of calculating residues, which you've had some experience of, you're getting better of, and both of them are poles, so we just multiply them by the factor. So since this is a pole at 0, we multiply by this, take the limit, this one's nice. This guy here is a harder expression. This is the factor we have to multiply by. We get some complicated expression. Finally get some answer for this. And to save work, we're not going to multiply out this complex number to see exactly what it is, because all we actually want is just the imaginary part of this thing. We want the imaginary part of this thing. So we just need the real part of this thing, not the imaginary part as I originally thought. We just need the real part of this thing. So we calculate the real part of this thing. We multiply together these complex numbers, this one and this one, and we find out it is equal to this. Yeah? And therefore, the imaginary part of this entire expression is this thing, and it's equal to the thing we're actually looking for, and that's how we do it. Yeah? That's how we do it. So apart from this extra little wrinkle of having to avoid the pole and remembering to put that contribution on the right-hand side, don't ignore it, it's not going to 0, then this is just the same kind of thing we've been doing before. So it isn't that much harder. It isn't that much harder. Yeah? Cool. All right. So there's another technique which is kind of standard, but probably does too much calculation the last couple of lectures. So we're going to move on to talking about singularities. And if I have time at the end, I'll show you yet another technique. And that's more or less all the standard ones you can possibly ask. But Usually these are the main ones. The other one is to deal with integrals involving some kind of root power and integrating low branch cut. And that's a rarer kind of question based on previous prelims. So if you get good at these techniques, that is one prelim question that should be pretty in the bag for you. Yeah? So it's worth getting good at this. This is one question, because every year there's at least one integral question. All right, people, that's it for today. Have a great day. I'll see you on Thursday. Bye-bye.